Hi, this is Yosuke Hasegawa from Institute of Industrial Science, University of Tokyo. Today, I would like to quickly introduce our recent work on optimal control of wall turbulence for dissimilar heat and momentum transport. The background of this work is fundamental question, are turbulent momentum and scalar transfer similar? So let's imagine that flow over the flat plate, and we also have some scalar distribution, which might be a temperature or some concentration of chemical species, and we have a turbulence. If you look at some certain location from the wall, we have momentum transfer and scalar transfer due to turbulence, which can be expressed by those equations. And because of these, we have wall friction and also wall heat flux. Reynolds proposed the Reynolds analogy, which suggests that non-dimensional form of heat transfer Stanton number is proportional to Cf, which is a non-dimensional wall friction. This problem can be also viewed from mixing length theory, which was originally proposed by Pranto. The eddy viscosity or eddy diffusivity are both basically scaled by the product of the length scale and the velocity scale of eddy. So from this theory, we can also predict that turbulent Prandtl number equal to 1. So both of them basically suggest that there is a strong similarity between momentum transfer and scalar transfer. In engineering, people develop a lot of different heat transfer surfaces in order to enhance the heat transfer. And of course, according to Reynolds analogy, we expect that the wall friction will also increase if you have a heat transfer enhancement, and thereby we have more pressure drop. This is a plot. The horizontal axis is a pressure loss, dimensionless form of the pressure loss, actually Cf times the Reynolds number in this case. And the vertical axis is Colburn J factor, which is similar to Stanton number, times Reynolds number. So the horizontal axis corresponds to pressure loss, and the vertical axis corresponds to heat transfer. So this black dot point corresponds to laminar flow. Actually, this point is independent of a Reynolds number. And some point, the flow becomes a transit to turbulence. And then with increasing the Reynolds number, actually, the line, this is for the smooth wall, eventually converge to Reynolds analogy as suggested by Reynolds. If you plot the different surface data, which can be obtained from existing literature, the plot look like this. So as you can see, Reynolds, the heat transfer enhanced. However, at the same time, pressure loss also increases. So ultimate purpose of heat transfer technique is how can we achieve a high heat transfer rate with a small pressure drop. So we like to achieve this red area. And this problem can also be analyzed from analogy factor. So if you introduce analogy factor, which is heat transfer divided by pressure loss, and it looks like this. And then again, so this figure, the horizontal axis is Reynolds number, and the vertical axis is this analogy factor. So in the case of the laminar flow for the flat surface, it's almost constant, actually exactly constant. And then if flow transit to turbulent, it approaches to 1. So Reynolds analogy holds fairly well at the higher Reynolds number for flat surface. And if you plot all the existing heat transfer surfaces, they will below 1. So again, we like to achieve analogy factor larger than 1. So in summary, as I said, there are various techniques for enhancing heat transfer, but they are commonly increasing not only heat transfer but also the pressure loss. Therefore, analogy factor is also less than unity. And the fundamental question is it possible to achieve a dissimilar heat transfer enhancement, which means that uh, amount of the enhancement of the heat is larger than that of the pressure loss. And the present study tried to answer that problem by applying the optimal control theory. So in order to make our problem simple, we consider fully developed turbine channel flow, which is basically flow between the two parallel walls, and the flow is fully developed and turbulent. And the flow is driven by a mean pressure gradient, and the flow rate is kept constant. And we apply a non-slip condition on the two walls. And for heat transfer, we also assume a uniform heating, which corresponds to the uniform pressure gradient for the velocity field. And we assume that the temperature is zero on top and bottom wall. Then governing equation for mean streamline momentum equation look like this. And also corresponding to energy transport equation look like this. Here, theta is the temperature, and the u is the streamwise velocity component. So their form looks very similar. And in our particular case, we assume that heat source inside the fluid is equal to a mean pressure gradient. So both in turn are same. In addition, we assume Planck number equal to 1. So under this boundary condition and this governing equation, mean momentum equation and mean energy equation becomes identical. Now, we try to control this flow by applying a blowing suction from the wall. So here, control input we call phi, which is in general function of space and time on the wall. So how can we find the optimal control input in our case? So this problem is very complex because this control input is an arbitrary function in space and time. There's a huge possibility or huge degree of freedom. So this is some schematic. So we have a huge degree of freedom for control input, and that is the input for our system. And then our flow system has a strong nonlinearity and multi-scale nature and a large degree of freedom. So basically, it's very difficult to predict the performance. And if you do simulation for specific control input, you can get the performance. But we don't know the optimal input yet. So the idea of optimal control is that we consider how my inputs should be changed in order to minimize my cost function, which is output. So naturally, in optimal control theory, you need to solve backward in time. So you assume some small perturbation in your cost function, and you will calculate how it propagates into control input. And once you get this information, you update your control input based on that sensitivity. And this sensitivity can be obtained by solving a joint equation of the forward problem, as schematically shown here, which solve backward in time. So in our case, we set our cost function as follows. So first term is actually phi, as I said, this is a space and time distribution of my control input. So this phi square integral over entire time and space means a cost for control. Second term is the CF, which is the pressure loss. So time average CF. And the last term is a heat transfer, which we want to enhance. So we put the minus here. So the meaning of this cost functional is I want to achieve high heat transfer with small pressure loss and also minimum cost for control. And in order to achieve optimal control, typically we introduce some time horizon in which this space-time integral to be minimized. Just specifically, we first solve the forward equation and then solve a joint equation. By solving a joint equation, we get the idea or sensitivity how to change my control input. And by iterating this procedure, you can get the space and time distribution of your control input, which we call the optimal input. But this time horizon is relatively short because of the computational cost. So we sliding our time horizon and continue this way. So this way we can optimize our control input for a long time domain. So now there are some question about the how long our time horizon should be. And there's a two, roughly speaking, there's a two category. One is a suboptimal and optimal. And the suboptimal is relatively easy. So we only consider very short time horizon. So vanishingly small time horizon. So in that case, actually we can obtain an analytical solution for my control input. So we don't need to solve a joint equation like this figure, because we only consider short-term dynamics, which is usually linear. On the other hand, optimal control, we have to solve a joint equation because we consider some finite time horizon. And then during that time, nonlinearity play an important role. So that you need to solve the joint equation. So obviously suboptimal is easy to apply, but optimal control will be more accurate, or we expect more control performance in optimal control. So we first apply suboptimal control to that problem. So this figure shows that the horizontal axis is the time and the vertical axis is the CF and Stanton number. And we normalize by uncontrolled value. So it's around 1. As you can see, the instantaneous Stanton number and the CF is almost around 1, and both of them changes almost similar way, which suggests that the Reynolds analogy. When you apply control, this ST and CF suddenly increase in this case. But what the interesting thing is that actually Stanton number is enhanced much more than CF. So specifically, heat transfer rate is enhanced 3 times, while pressure loss is only doubled. So this is a visualization of turbine channel flow subject to suboptimal control. So this white contour shows that the second invariant of the deformation tensor, so which is vortex core. And you can also see some color on the bottom wall, and the red region corresponds to wall blowing, and the blue region is wall suction. So you can see that the large area we have a blowing and a large area of wall suction, and in between we have a vortex region. As you can see, this suboptimal control input is something like almost uniform in spanwise direction, and then followed by another spanwise uniform wall suction. And this wall blowing suction is propagating to downstream. So if you look at from the spanwise direction, it looks like this. So now you see that control input is traveling downstream. And here we have a wall blowing both sides. And we have a quite large difference between the velocity component and temperature. By the way, this velocity is a streamline velocity. So from the viewpoint of the governing equation, those two are quite similar, as I mentioned earlier. But the response of the velocity field and temperature field are quite different. Especially you can see that here is very high velocity region, doesn't show in a temperature profile. But one problem in suboptimal control is that if you extend your domain, then the control input is also has a longer length scale. So always inside your domain, you have a one pair of blowing region and suction region. So this means that suboptimal control input depends on the stream-wide domain size. So it's not a universal or global optimal input. So we also did real optimal control for a finite time horizon. So in this case, as I mentioned before, you need to solve the joint equation and then update the solution. And what's the interesting thing in this case is that actually we also have a traveling wave-like input, but in this case, the wavelength is shorter than domain. And actually we also confirm that this wavelength is independent of the domain size. So here we show that the control input at the top wall and bottom wall. And the blue region is a wall suction, and the red region is a wall blowing. As you can see, the control input is in a varicose mode. So blowing region corresponds to same X location each other, and suction also the same. And if you look at this movie, you can see that control input is propagating downstream. And according to optimal control, we obtained that lambda x is around 300 in wall unit, and the phase speed of this traveling wave is around 5, again in wall unit. So let's compare the control performance for suboptimal and optimal control. So this is a suboptimal control result, and if you do optimal control, actually Stanton number is not that enhanced like a suboptimal control. But more interesting thing is that in this case, CF, so wall friction, is reduced from the uncontrolled value. So in this case, we achieve a simultaneous achievement of heat transfer enhancement and pressure loss reduction. So heat transfer is almost doubled and pressure loss is reduced by 30%. So if you calculate analogy factor, which is the ratio between the Stanton number and CF, actually optimal control input results in a higher value, which is almost reach 3. Now look at where our results are located in this CF and Stanton number map I showed before. As I mentioned, most of the existing heat transfer surfaces is below this analogy, Reynolds analogy line, and our suboptimal and optimal control results located here. So they achieve analogy factor higher than unity. And if we also plot the analogy factor as a function of Reynolds number, our results located here, which is a huge improvement from existing surfaces. Now there is one question that the optimal control we obtain from optimal control theory really optimal. This is somewhat a weird question, but optimal control theory is gradient-based method. So if we have multiple local minimum, the resultant optimal control input will be stacked to a local minimum. And another issue is that we always apply optimal control theory with some finite time horizon. So in this particular case, T plus, which is in wall unit, is around 100. And this time is much shorter than a period required for a flow to reach a new statistically steady state. So that means that our control input is optimized only for relatively short-term dynamics. And it doesn't take into account long-term dynamics. So we still don't know whether this optimal control input is really globally optimal. So we did another parametric survey by systematically changing the wavelengths and the phase speed of traveling wave. So in this case, my control input, we assume that the stream-wide traveling wave. And there's 3 parameters. One is the amplitude and wavelength and phase speed. And in general, we keep the amplitude around 5%, which 5% of the bulk mean velocity, which is also obtained in optimal control theory. And we mostly focusing on effect of the wavelengths and phase speed. And boundary condition and also the governing question is also similar to the previous optimal control problem. So we assume a uniform heating inside the fluid, which is equal to mean pressure gradient, Prandtl number equal to 1. And on the wall, we assume non-slip condition and constant temperature. And we systematically change lambda x, which is the wavelengths here, and also the phase velocity UP. And we did approximately 350 cases, a lot of DNS. Now, this is a summary of our results. Horizontal axis is the phase speed of traveling wave, UP, and the positive means the downstream traveling wave, and negative is the upstream traveling wave. And the vertical axis is the wavelength, normalized by channel half height. Oh, by the way, this UP is normalized by bulk mean velocity. So first, we can see that upstream traveling wave, we have a drag reduction, which is also reported in previous work. And also UP around 0, so this is a standing wave. We have also drag reduction slightly. And for downstream traveling wave, there is some stabilizing effect. And this is also agree with the existing literature. And you can also see that between 0 and 1, there's a large area where CF is larger than uncontrolled value. Typically, it becomes 4 times more than uncontrolled value, so which is a quite large enhancement of the wall friction. So pressure loss is also increasing. If we look at the Stanton number, we can also see peak around the same region. But if you compare carefully this one, actually heat transfer enhancement is larger than the CF in this region. And another thing is that if you look at the upstream traveling wave, we don't have a reduction of the heat transfer like pressure drop. So in the case of the pressure drop or wall friction, we have a smaller value than the uncontrolled flow. So we have a drag reduction, but the heat transfer is actually higher than uncontrolled flow. So here we have some sort of the dissimilar effect already. But if you calculate the analogy factor, peak is actually located here. And this global optimal we call is around lambda x equal 1.12. This lambda x is normalized by channel half height. And UP is around 30% of about mean velocity. What's interesting thing is that what we obtain by optimal control is very close, not so bad actually. The phase speed is exactly the same, but the wavelength is slightly overestimated. This is probably because, as I mentioned before, optimal control theory only consider limited time horizon. On the other hand, this parametric survey, we can really find that global optimal. Now, next question is that what control mechanisms? So according to our the previous slide, we identify the global optimal traveling wave mode, which is shown here. And wavelength is around 200 in wall unit, and phase speed is around 5 in friction velocity. So we decided to analyze more in detail that how this similarity achieved. The starting point is that we use Fukagata Iwamoto Kasagi identity, which is so-called FIK identity. So friction coefficient can be expressed by the sum of the laminar contribution and turbulent contribution. And the turbulent contribution is weighted Reynolds shear stress. And similar way, in the present condition, the Stanton number also written like this. As here we assume Prandtl number equal to 1. So the laminar contribution becomes exactly the same, and also the this Reynolds shear stress is replaced by a turbulent heat flux. So if you consider difference between Stanton number and the CF, which we call dissimilarity, then this will basically caused by this term. So the question is how this term is generated in the case of the control flow. In order to analyze more, we decompose the instantaneous velocity field into three components. The first one is a mean component, which is a mean in x and z horizontal direction and also time. So this mean field is only function of y, which is wall normal direction. And then we apply traveling wave so that we average in this window, which corresponds to one period of our traveling wave. And this window is traveled with the wave. So in this frame, the control input looks steady, and the resultant coherent fluctuation is also steady in this window. So that component we call coherent component. And as I said, this is periodic and moving at the same speed as the control input. And finally, we have a dash dash component. This is other fluctuation, which is incoherent and unsteady components. So conventional turbulent fluctuation can be written by the sum of this coherent fluctuation and random fluctuation. Now we decompose the this contribution to dissimilarity into a coherent contribution and random contribution. What's interesting here is that this coherent contribution only has a 38% of the total contribution, and 62% is coming from random. The reason why I said interesting is that because our input is a coherent input, so it directly affects a coherent component and only indirectly affect the random component. But as a result, random field is more modified or more contribute to dissimilarity. So that's the reason why I said this is interesting. And if you look at the integrand, and then also plot as a function y, coherent contribution occurs very close to the wall. On the other hand, random contribution has a more wider profile and which has a larger contribution even away from the wall. So their mechanism seems quite different. So first we look at the coherent contribution or coherent field. So here we apply wall suction at the cycle 0, and then here on both end of the horizontal axis we have a blowing. And as I said, this frame is moving with the wave downstream. And this one is a temperature field, and this is a wall normal velocity component. And if you look at close to this near wall temperature field, because of the wall suction, high temperature fluid going down, and here is we apply wall blowing so that you can see that the low temperature fluid goes up. And since this traveling wave interact with the bulk flow, we can also observe some spanwise roll generated close to the wall. And similarly, if you plot the streamline velocity component, this one is quite different from the temperature field. As I mentioned, the governing question of the temperature and the velocity field are similar, but we can clearly see that their response are quite different, especially if you look at slightly away from the wall. We have a positive and negative contour, which is we don't see in a temperature field. So this is because that the wall blowing suction generates additional pressure fluctuations, and that only accelerate velocity field, but does not affect the temperature field. So that's a fundamental source of dissimilarity. And because of this difference, we have a theta tilde minus u tilde distributed like this. And then if you multiply v tilde, we eventually get a coherent contribution. As you can see, we have a strong peak close to the wall, which corresponding to this peak. Finally, we also look at the random contribution, how it's generated. So this is uncontrolled flow and controlled flow. And as you can see, this red area is positive contribution drastically increased in the case of the controlled flow. In order to analyze how this random contribution is generated, we look at the budget of this random contribution. It's a little bit complicated, but eventually we found that this production term is a dominant term. So if you look at the budget, you see that here is a strong peak positive contribution. This is coming from the production. And this location agree fairly well with the peak of random contribution. So let me summarize that the mechanism of a dissimilarity induced by traveling wave like wall blowing suction. So as I say, our problem is the flow over the flat plate, and we apply a streamwide traveling wave like wall blowing suction. And because of this traveling wave, as we saw in our previous slide, that we generate some spanwise flow. And this will cause dissimilarity between the velocity field and scalar field. And that contributes to 30% of the entire dissimilarity. And this is not end of the story. But if we have some dissimilarity in the mean field, this will amplify by random background turbulence. Specifically, this production term is a dominant term for generating additional dissimilarity. Therefore, we have more dissimilarity between the velocity field and temperature field. And that contribution is larger than the coherent contribution. So what we found is that overall dissimilarity is caused by a complex interaction between the coherent and random field. So although our input is coherent, but this coherent input indirectly affect the random contribution like this way, and then we get more. And another important thing is that by applying optimal control theory, we can get such control input without prior knowledge. So we can get somehow the mathematical optimization tells us that the optimal input. So let me conclude my talk. We apply optimal control theory for optimizing space and time distribution of wall blowing suction for achieving a dissimilar heat transfer enhancement in a fully developed turbulent channel flow. And we identified the global optimal traveling wave mode, and which has a streamline length scale of around 200 in wall unit, and the phase speed is around 4 to 5 in wall unit. And interestingly, coherent contribution is only 38%, and most of the contribution is coming from random contribution. So which suggests that the indirect interaction between coherent input and random turbulence is quite important in this case. And the coherent contribution is caused by continuity constraint. So as I mentioned in a previous slide, it's basically generated by pressure gradient. And pressure field is, of course, determined so as to satisfy continuity. On the other hand, random field is triggered by dissimilarity of the coherent field, and this amplified by turbulence. The contents I talked today is based on our previous papers. So if you are interested in, please access those references. So that's all from me this time. If you have any question, please free to contact me. Thank you for listening and see you again.